Hi everyone, welcome to the fifth and final webinar in our Knowledge Zone series for 2026. And welcome to those joining us today for the first time. So today we welcome our speaker, Stijn van den Eeden from Babbage Consultants. Look, this series, for me personally, it's been a great series of reminders across all these sessions. I've been reminded of the common language that is shared across engineers, facade engineers and architects and designers. It doesn't always filter through to everyone involved in the process of designing and building. But the shared common language means that we know what to ask for accurately, and that can only be good. We've seen case studies of failures, not just failures on site, but the process failures or systemic failure of poor decision-making in material or design, or poor quality control or lack of it, as we saw in the glass manufacturing practices. The phrase came up, was shared by Brian, I think, you get what you inspect, and that one has stuck in my head. Construction monitoring. As a sort of an aside topic, but the construction monitoring is an easy target to remove cost from a construction project, but the consequence might make that decision a false economy. I do look at construction monitoring as a tide that lifts all boats, and that can only be a good thing for our industry. Bring back the clerk of works? Not sure. Let's move on. So this webinar is hosted by Proclimer, but it's not about Proclimer. I said that yesterday, and it did feel Proclimer heavy with Jesse's presentation, but ultimately it's been a platform for industry experts to share knowledge, science, learnings, mistakes, and opportunities. And all of these presentations are available on Proclimer's YouTube channel. So now we welcome Stijn. Apart from chairing the Society of Facade Engineers, Stijn is an associate principal of Babbage Consultants, and he brings a wealth of knowledge in facade engineering, window design, and enclosure design, which is inclusive of subgrade basement and roof. And the topic today, warm roofs, do they last? Stijn, I advertised this session yesterday at the end of Jesse's presentation, and I think I've already answered the question for you. My answer to your question is yes. I'm sure there's some more useful information that you can add, and so I look forward to your presentation. We'll see how we go, but I'll bring some specific questions or maybe just ask for clarity during your presentation, and we'll stop with around 10 minutes or so to go at the end for some questions. And if our audience can please use the questions tab in the top right-hand corner of your screen. That's the one with the question mark, if that's not clear. And yeah, Stijn, if you are ready to go, over to you.
Yeah, thanks so much for the introduction, John. Yeah, so warm roofs, the reason and the start for this presentation was really all about, look, we do enclosures. There was a lot of focus on facades, but in fact, one of, if not one of the most emerging trades coming up is the section of warm roofs. And here in New Zealand, it's relatively new. And I'll talk a little bit through different items, the theory behind it, the different variations you have, what is important, the things we see that go wrong, and in fact, what we can do both as architects, as builders, to really minimize the risk. Because, and that's the most important part, maybe, warm roofs is really future music. It is what we will end up specifying, using, installing almost as a standard over time. So I'll give you a little bit of history for that first. Oh, there's a little bit about me, very quickly, some pictures. I've had good fun here in New Zealand for 16 years, building things like Open City Mission, Christchurch, Justice Precinct, but also internationally before that. I worked basically on 5 continents with jobs in, I see there, Malaysia, Algeria, but also in Latin America, in Tokyo, and so on. Anyway, back to the topic of today, which is warm roofs. So the history is really in the 1930s, and slightly before that even, it started, flat roofs started to become pioneered. And that's because of mostly aesthetical reasons. New architectural streams, like one of my favorites, the Art Nouveau, for instance, which comes from the area where I'm from originally. They really wanted a different look, a little bit what you see here, with flat roofs that they could build gardens on, that were kind of minimalistic and less visual. So at that stage, it was all, quite about aesthetics and not so much functional. Now, 1960s, there was an early adoption of these flat roofs more throughout the world, but I think it really didn't take off seriously until the oil crisis in 1973, because then all of a sudden it was all about insulating our roofs. And at that same time in the 80s, we also saw quite a surge of in the technology of new materials, such as foam insulation, right? And then we flip a few decades and we go to, let's say, the early 2000s. And what I'm showing here is a little bit of history in Europe of energy requirements. And that is all, of course, with the vision of meeting Paris Agreement by 2050 and being net zero. Now, Europe has a bit of history there and has been on that track for quite a bit. So they started with what we call energy performance certificates. That basically means that any house that you're trying to sell, or you rent it out even, you need to show how energy efficient it is. Because of that, of course, there was a push in the market to be able to show better numbers, and people started to insulate naturally as a consequence of that. And warm roofs quite quickly became much more popular. Now, you can see from this timeline that, in fact, the ambition in Europe is quite high, with nearly zero energy and full zero energy for target and public buildings by 2028. All of that is quite close, of course. But as a consequence, warm roofs are becoming very often the only option for, let's say, public and for public or big commercial buildings, right? Here in New Zealand, unfortunately, we're a bit behind, although there were really good, I think, roadmaps issued. In fact, the biggest change by far for New Zealand came when Section H1, energy efficiency of the building code, was updated a few years ago. And that now requires an R value of 6.16 roofs. That by itself is great. It really puts us back in line with where Europe was. Unfortunately, there's more things we need to do here, like managing our internal moisture, which is covered in E3. And very unfortunately, it's very archaic, very old-fashioned, and not up to date anymore, especially now that H1 is quite high performing already. So something very specific, and if there's probably one thing I really want everybody to remember from this presentation, is probably this slide. It's about our climate. And we always say, well, whatever we do, they'll do it somewhere else as well. But in fact, in New Zealand, we have an oceanic temperate climate, and it's very different than a lot of, let's say, warm, moderate climates you find all over the world. I've just popped in a little graph here, Auckland, Wellington, and Christchurch's relative humidity throughout the years. So you see 12 months, and you see the relative humidity on a scale up to 100%, and how that fluctuates throughout the year. Now, I've taken other cities in the world in warm, moderate climates, and I've mapped these out against what we have. And for the Northern Hemisphere, of course, I've offset it by 6 months. So we compare the same, let's say, climatic months against each other. And funnily enough, if you see all of these, they all have a drying season at some stage in the year. Even Melbourne is in there. You can see Melbourne has a very dry winter period. But then here in Auckland, we are constantly sitting around at 80 or even 85% relative humidity. Now, the message here is very clearly that we can't just count on drying out our buildings with external air the way they will do it in other climates, because at some stage that moist air we bring into the building has a very limited capacity of absorbing more moisture, right? And that means that our ventilation is less efficient, but that also means we really need to think about the building physics more here in New Zealand than probably anywhere else. So what I'm going to talk about is a little bit building physics, which is the interaction between heat, moisture, and air, and how it travels through our building skin, through the walls, through the roofs. I want people to understand there is a difference between what a wind barrier, an air barrier, and a vapor barrier are. Wind barrier really has to do with the old wind wash, where wind was blowing through insulation. We don't see that much anymore. Nowadays, we always have an air barrier on the outside that stops the air going through. But then we also have vapor barriers, which really try to control the moisture going or moving between in and out. One simple rule: if it's damp closed, it's also airtight, but it's not the other way around. Vapor barriers we measure in things like equivalent air thickness and a vapor resistant diffusion factor. I'm not going to go too much in the technical details of this. One general rule that comes back: cold air cannot absorb as much moisture as warm air. So that's quite important when we talk about roofs, and especially the cold roofs later. The thing we are measuring, or what we are assessing our systems for, is condensation. And in fact, to make it easy now, I'm going to talk about 4 types of condensation that we see occurring. And the first one is the one we see on the outside. On the inside, the surface condensation. So very basically, it means you have a lack of insulation. You'll see condensation on the internal temperatures. The next one is the one on the outside, which we see, or occurs on the outside, which we see, for instance, in night sky radiation. Let's say you have a profiled metal roof. Overnight on a wintry day with no clouds, a lot of the heat in that metal roof will radiate out into space and nothing comes back. Because of that, that temperature of that cold roof over that metal will go even up to less than 10 degrees, less than the air temperature. So that becomes a perfect surface to have condensation on, right? Look at the picture. You see the car standing there. This is what a car looks like in the morning when it stands outside and it's been exposed to the night sky. You'll see the condensation on it, on the car, because it's the coldest temperature. If that car would be parked underneath a polycarbonate roof, for instance, it wouldn't have any condensation. It would be protected. You don't have that radiation. The third kind of condensation we need to talk about is interstitial. So we've had condensation on the outside and the inside, but you can also have condensation inside your building envelope, so inside the wall or the roof. And within that interstitial condensation, some will happen because of diffusion, some will happen because of convection. Diffusion means you just have a different amount of vapor on either side of the layer, and slowly it will migrate from one side to the other to look for balance. While in convection, that's all about leaks. You have a certain area where the air tightness is not well preserved, and air will be able to travel through, take moisture with it, and it will at some stage encounter a lower temperature and condensate. Very different principles. Diffusion will happen always, right? Because we always have a slight difference between in and out, but it goes slowly. It also goes over big surfaces, but it goes slowly. Convection, that's a real problem, child, because convection can go very quickly, uh, depending if that airflow is not is quite significant. You can have local damage, local condensation in quite big numbers. I have one more condensation principle, which is the inverted conversation, which basically can happen only in the summertime. Now, for warm roofs, not that common. You need basically three conditions for this to happen, and all three needs to be fulfilled. Otherwise, it's not going to happen. So one is you need moisture in that insulation package. You need quite significant convection, so leaks. And thirdly, you still need a good vapor barrier there, because that's very often the trigger for the condensation. So don't worry too much about inverted. Think about the other one, especially the interstitial condensation, and how we're going to resolve this. I'm still not done with the theory, but we're almost there. It's really about roof typologies. Here you see a picture of, let's say, the most common roof here in New Zealand. Cold roof, it's pitched. It means we allow water to basically be drained off the surface, but in fact, we provide means of air and ventilation underneath the roof, so we can basically ventilate that area, we can dry it out. The focus of these roofs is, hey, you need a minimum slope. We make them rainproof, but the air tightness should sit on the warm side where the insulation is, in combination, if necessary, with a damp open on the roof. This is the system we all know, right? Now, flat roofs, and I really like this very confusing picture, because this is what we call a flat roof, but obviously it's not. It's made up with membranes. The definition of a flat roof is basically a roof with watertight joints. So the water resistance does not come from deflecting the water or draining the water out. It comes from having a fully water resistant layer with watertight joints, and then at the same time provide air tightness and damp proof as well. So the principles of this roof, or keeping this roof healthy, is very, very different than what we're used to with cold roofs or pitched roofs. In this case, we don't want ventilation. We don't want to dry out the principle. And the most important rule is probably there is no mechanism to recover from any water getting in there. So we need to avoid high moisture in these roofs, because once it's in there, it's not going to drain out anymore. And it's really not made to, even with diffusion, to evaporate out of that layer anymore. So in the flat roofs, we have the warm roof, which is the one we're talking about today, and very close to that, the green roof. Basically, they're very similar, these two. With a green roof, and you see here a picture of a job we did, this Auckland Library, basically has a green roof on top. It's very similar. You basically add additional soil and you can plant plants on top. And the products are slightly different, but the roof itself, the principle is very similar. One of my favorites is the inverted roof. That looks like this. The only difference with the one before, with the warm roof, is that, so this is the warm roof, is that the weather tightness that in the warm roof sits on top of the insulation. We've taken it out and we've put it underneath the insulation. Now, a lot of people will question immediately and say, well, then means that the rain is going to go through the joints of the insulation and basically cold bridge that whole insulation. And that is absolutely true. But measurements have shown that the amount of water that does that and that really flows through that insulation is very limited. So although we lose some efficiency, that efficiency is not that significant for the system to really not to be considered or to say it's not functional. A few things why I like inverted roofs is that basically the weatherproofing, the membrane here sits underneath the insulation, so it's not exposed. It does not have to cope with UV radiation, hence also not much movement, because your entire roof is covered and stays more or less at the same temperature. So the movements in this whole system is quite a bit less. You do need ballasts, as you can see on the left-hand side. With warm roofs, that is optional, but in this case, with inverted roofs, you need it, otherwise your insulation will basically fly away. The only insulation material you can use in this kind of inverted roof is XPS. Don't use PIR or any other material. They will all absorb quite a bit of moisture over time. XPS is the only product that we would recommend. I was in a conference for wind engineers a few months ago. They are not that friendly to inverted roofs because they fear a bit the ballast to be picked up and flown away. And to a certain extent, that is true, but that's why we normally build little parapets around that roof as well to stop that ballast from flying away, right? And then a few ones that I don't like. This is basically a flat roof version of a cold roof. So you have a little bit of ply with membrane on top of it. And you depend on, like we do for cold roofs, on the ventilation underneath to deal with any moisture and condensation that may happen there. Now, I've got 5 reasons why I don't like this system. But the most important one by far is that in the winter time is when you need this system to work. That is also the time when, in fact, your cold air has very little capacity to even absorb moisture. So the timing is off. That moisture that will come from inside and will migrate through this roof will then have to absorb by, hopefully, ventilation. We always think we have it, but we don't have recommendations or we don't have guidelines in New Zealand on how much ventilation you need to provide. We have these, or we copy these over from the British standard, who does give us a certain airflow. But in fact, there are so many risk points in this specific buildup that it is quite a dangerous scenario and need to be managed very well. Another one that I want to, that in fact falls in the same category as well, that has quite a lot of risk, is when you have a concrete floor and you try to insulate it from the bottom, and then putting a membrane on the top, or weatherproofing membrane. It can work, but there are a lot of restrictions, a lot of conditions that have to be fulfilled. So the concrete itself will contain, especially when it's cast on site, will contain a lot of moisture. That moisture dries out, but very slowly. So approximately 25 mils a month. That means 200 mil concrete slab will take 8 months to dry out. If you fix a membrane on top of that, there is a lot of risk that that membrane will pop off, that the moisture will basically create bubbles or whatever that, or other failures to that membrane. In this system, you'll depend a lot on drying out to the inside. So in fact, if you put a vapor barrier to the bottom of this, you completely seal your whole package that then contains a lot of moisture. So there is a risk for mold there. Like I say, it is very difficult. It can be done better on existing buildings where you have an existing concrete floor slab, because normally the moisture content of these are quite a bit lower already. And then we have a few, let's say, that are more like question marks. This one is one we see at times in remediation. You have an existing, let's say, floor membrane. You put additional insulation on top in another membrane. In case you do that, I won't say it's not possible, but we would recommend, we will simulate this, but we would recommend, for instance, that the new insulation is about 1.5 times the R value of the original package to avoid any condensation in this buildup. And then the last one is a compact roof. Compact roof, I haven't seen much in New Zealand. It's more popular with modular construction, for instance, but it's an interesting one. And I put it here because I was bad-mouthing the cold roof buildup before with the air gap we have there and the ventilation. So one could argue, well, why don't we get rid of all that air and just seal the whole thing up? So maybe that will help. And in fact, it is possible. In like I said, I've seen it in modular construction, but there would still be quite a few conditions we add to this. For instance, we would require a minimum slope on these roofs just to avoid too high risk. We would not recommend dark membranes, black membranes, because they will create potentially issues with that inverted condensation that I said before. And there's a few more items. But if anyone ever wants a good challenge and is keen on getting a compact roof, come and talk to us. Finally, I'm gonna start talking now about the hero of the story. And the hero of the story of a warm roof is really the vapor barrier. The vapor barrier is the layer that sits underneath the insulation, and that basically protects that insulation from any moisture, any vapor coming from underneath, from the building where people live, which is in fact the vapor barrier, and the performance of that product is in fact more important almost than the top layer. Both are important, don't get me wrong, but little picture here of what we sometimes as designer dare to do to installers. You see a perforation going through. This is a vapor barrier asphalt built, and you see all the detailing. To provide perfect air tightness in conditions like this is hard, but hey, this is a really good example of how it should be done. So that installer should be pretty proud of what he's done here. So what are the functions of the vapor barrier? Like I said before, by far most important is avoid internal condensation. Stop moisture from rising up into your insulation. Sometimes we forget about that, but especially on glued system, if you have a perfect vapor, or let's say air tightness in your vapor barrier, you seriously reduce the wind pressures on the roof membrane, on the top membrane, because the suction of the wind, you will basically distribute it between all the layers. And the vapor barrier is in fact a very important one there. And then finally, and I want everybody to forget this immediately again, it is sometimes used for temporary waterproofing, but it should not. A vapor barrier is not waterproofing. And the problem is, and we'll talk about this later, but the problem is that if you would have water while you install your roof, you're probably already overdoing it. This is not how a warm roof should be installed. In Europe, we classify vapor barriers by the amount of the equivalent air thickness. So how much vapor it basically stops from transferring from one side to the other. And it looks a little bit like this, with E1 being the lowest and E4 being the highest rating. Fortunately, most of the suppliers here in New Zealand use aluminum-faced bitumen, which is the best product and basically will comply in most conditions. Considering this rating from E1 to E4 for vapor barriers, we try to classify that against various conditions. One being, what building are we putting this warm roof over with? depending on humidity classes, which let's say the standard ones being class 2, buildings unknown class 3, and then the worst ones like swimming pools and everything is basically a class 5. We also look at the substrate, with concrete being slightly higher risk than plywood because of the moisture that the concrete already contains. Then we look at the insulation. Do we use PIR or XPS or mineral wool? Mineral wool is slightly worse off. Can't deal that. It's a little bit more compressible. It's not the best product. If we can, we would try to stay with PIR. And then finally, we look at the fixing. Is it all glued together or is it mechanically fixed? Now, note these 4 red crosses there. So if we are in very high or on the roof of very moist buildings like swimming pools or sport halls, we would not recommend mechanical fixing at all. And that is because all our fixings will go through the vapor barrier and create small leaks, right? So if you have a lot of moisture down there, you will depend a lot on that vapor barrier to be very, very resilient. And we wouldn't recommend it unless it's glue fixed. A few details. Following up from the theory, you need to understand that insulation that sits there needs to be fully sealed. We seal it on the top with a membrane, on the bottom with a vapor barrier. But in fact, when you go towards the parapet, these two need to close. They need to seal that package of insulation as well. So some supplier, rightfully, they put this little detail in there where you have a 50 mil overlap between the vapor barrier and the membrane above. I think this is really good practice. It kind of avoids, especially on parapets where you can have already quite a bit of moisture, it avoids that any moisture would migrate through the edges of the insulation into that package. Another detail we'd like to talk about is when you have profiled metal and they put the vapor barrier on top of this, a little bit like this. And then they come to the end of the roll and you see that vapor barrier is basically bridging the hills between the profiled metal. So if you then continue with the next roll, it becomes very difficult to glue that on and see that it's still airtight. So we recommend to use a little steel plate to basically cover the hills so that that joint is well supported. A final detail here is about penetrations going through. And when you see the penetrations like this, you assume that there'll be some condensation. So it's very important that all these penetrations are very well sealed as well to avoid any water potentially reaching the insulation through that gap. I've seen a job, for instance, where the penetration had exactly where the insulation was sitting. It had a joint there, which of course would then allow additional moisture to travel through that joint into the insulation. Right? New Zealand, any good, let's say, building code and literature. Our building code, unfortunately, talks only about thermoelastic materials like EPDM and butyl. And there was very little available until the WMAI basically published a few documents. Now, I would recommend you go on their website and look at the code of practice for the reinforced modified bitumen membranes. The single ply membranes is due to come out soon. I know I have a little bit of a preview what it will look like, but that's a very interesting document that will tell you a lot about detailing, installation, and so on for the single ply membranes. The options, maybe to give you a quick idea, in thermoelastic, we have EPDM and butyl rubber. This is what the acceptable solution will read. In fact, really good products, but the main issue, in fact, they are trafficable, they're quite UV resistant, but the main issue we see constantly with them is the the jointing, the membranes. So they're either glued together or there's some other systems there, but you depend a lot of labor to do a really good job with these products. Then we have the thermoplastics ones like the PVC, Sika. We have TPOs and KEE, like Fibertite. These products are quite thin products overall. So you basically have only one layer of defense. Especially KEE has quite good durability, I find. But the other ones are used throughout New Zealand now as well. Bitumen is, of course, the oldest product, and you can see how it's being burned there. And liquid applied. Liquid applied depends again a lot on labor to have the right thickness that has been applied in the right conditions. It's probably more complicated than a roll system, so it would need very, very good QA for it to work. A little bit about LCA, because I think at times it is being forgotten about. So we typically would say for a roof, we would like to have 60 years with 20-year cycles. Bitumen has the advantage that, in fact, every 20 years, you could overlay the existing bitumen with a new layer. While adhere thermoplastic and thermoelastic, because of its adhered, it would need replacement not just of the membrane, but also the insulation below that. That comes at a much bigger cost, of course, and you'll have to open up the roof again. The technology as of today to fully overlay these thermoplastic and thermoelastic materials is not there yet. So I think bitumen has a bit of an advantage there. Mechanical fixing, so any perforation when it's been opened up or taken out, you need to go back to the insulation underneath and seal that vapor barrier. And then for products themselves, there are several recycling opportunities for, let's say, PVC and bitumen, yet none of that yet in New Zealand, as far as I know. How much time do I have, John? Still a bit more.
Doing good.
Okay, I keep going. Then a little bit on pathology, what we see going wrong at times. A typical one is primers and the adhesion on, let's say, concrete systems. I got a few pictures there where you see concrete of poor quality, concrete maybe cured when it was too cold or too hot, and it's kind of dusty, doesn't adhere well. Primers being adhered when it rains or just after the rain. We see a correct application of the primer sometimes doesn't work. So if you prime a concrete floor slab, you prime only the area where you're going to glue on insulation the very same day. You need to let it flush off a bit, then you're okay to go. But if you come back the next day, you need to reapply the primer if you didn't finish the work. Very often rain, and I've spoken about this before, but warm roofs, ideally you want to protect them when you install them, right? You kind of close all these layers together. You have products that are quite sensitive in application and everything. And because it doesn't dry out, you always run the risk that overnight it rains a bit, that water sits there. And what you don't want to do is then close that off with all the water inside that package, because it's going to affect the materials over time. Another example of something that came across our desk quite a few years ago was a buildup of a swimming pool in a retirement village. And I'm going to very quickly give you an idea of what it looks like, but it's basically profiled metal with an air cavity underneath. There was a roofing membrane there, some insulation, and then we had an aluminum faced bitumen vapor barrier. Then there was a layer of plywood, and you could see all of this was fixed through the insulation into the ply. The ply was there really to take on the fixings of the whole roofing system. And then the architect did very well, basically trying to protect this by then adding a cavity, adding another vapor barrier, which was the Intello from Proclima, and then a service cavity. So the question was a bit like, hey, is this going to work? When I looked at it, my first thought was like, well, I really hope it does, because I think every single product or everything they could potentially specify here is included. So if this doesn't work, I don't know what else we can do. But then looking at the simulation, so sorry, on the left is the detail, on the right is basically what we build up in our WOFI study. And we run that for 10 years to see what humidity is, how the durability of the product sits, and so on. But basically, when we looked at the result, one thing caught my eye, which was the moisture content in that ply. So remember that plywood sits in between, sits here, about here, sits in between or just underneath the insulation. Now, what caught my eye was the fact that that moisture content in the ply went down over 10 years, but almost as a linear curve. And that's very unusual. So it meant that that ply in the original content, moisture content in the air, was drying out, but extremely slowly. And if you then look at the buildup again once more, you basically see that that ply was sitting between some aluminium faced or the vapor barrier on top of it and the Intello underneath. So it was really stuck between two vapor barriers, like as if it was packed in a little bit of plastic, right? And rather than having two vapor barriers, we propose to remove one of the two. And these are the two scenarios, what that would look like. So if you remove the external vapor barrier, this is what was happening. And you could see it become seasonal, right? And if we remove the vapor barrier to the inside, the moisture content immediately dropped, because this is a swimming pool, but remember that internal temperature in that swimming pool was all year round, 24/7, quite high. So that's also why it has, in fact, a little bit of capacity to dry out to the inside. And we spoke with the suppliers, and basically we chose the top solution here. I think that was the one that was the one. Yeah, it was finally built this way. If, and I don't want to be talking too negatively, but if things go wrong, of course, we talk about molds, we talk about moisture, we talk about durability of product. It's one of the things that I take quite close to heart, that I feel is really a problem here in New Zealand. We have probably the cleanest and best air of any, for big cities. Here in Auckland, for instance, the cleanest air of any big city in the world. Yet respiratory diseases in New Zealand are just through the roof, and we're almost leading that worldwide. So something is clearly off. A lot of that has to do with what I showed in the beginning, that really high relative humidity, which just makes it very difficult for us to dry out the houses. It's not the only reason why we have so many respiratory diseases in New Zealand, but building and the way we built is definitely one of the reasons why. So I think, especially now that H1 energy efficiency has become more stringent, I think it's really important we talk about moisture and how it's managed in our buildings, because otherwise this thing will only become bigger. And lastly, I do want to give some ideas basically to our architects who specify warm roofs, and to our builders and to our clients as well, on how I think we can very easily mitigate any risks with warm roofs. we've seen quite a lot of failures in warm roofs already, although the technology here has not been used that much. But it's important to maybe do simple things that can help us. The first one is compartmentation. Compartmentation of warm roofs is a standard in Europe. So what you do basically at the end of a day's work, you basically bring down your membrane and you connect it back to your vapor barrier, so that all the insulation that sits, in this case on the left hand side, is basically nicely captured. If overnight it rains, yeah, you've already protected your products, right? You're not gonna have to check on that. You're gonna have to dry it out, and sometimes, of course, we know nothing happens, and that rainwater just sits there forever. Compartmentation is then also very useful for if architects specify it, but also request as built drawings afterwards. So that means that if you're going to have a problem, it's going to be restricted to a relatively small area, but you're also going to know which area you're talking about. I would always recommend areas where you have lots of perforations going through to also compartment these areas anyway. Next safety net is really to do with sensors. There's really quite a few options available. Very sensors that can be built into your roof. They sit there for 20 years and basically give you an idea of what the content of the moisture is in your package. There's really nice advanced systems from Canada that have a fully active monitoring of the system, but even including location. Now, of course, that comes at a price, so it's not going to be for everyone. But I would say, especially if you're thinking of doing a green roof, I think this is a beautiful solution to build in first, because if your roof ever leaks, you're not going to have to take all the dirt and the trees back off. You're going to know exactly where it sits, right? And then two other options, and this is my last slide, so we've made it to the other side almost. It's really about infrared. We have a drone here that we can fly above buildings. What we do is we keep that hovering about 30 to 50 meters above the building, take a straight shot down. There's certain conditions. You can't do that all the time. You need to have certain temperature differences and so on. But this thing basically figures out, measures if any water would be trapped. Now, it's a relatively small cost. It's the same as an inspection, but it goes straight into the performance of the roof. I think an architect can specify to say, hey, the first winter after the installation, plus after 5 years and 10 years, we do tests like this. I think these are great solutions that would reduce the risk quite a lot. And like I said, it's at a minimal cost. And of course, we have the electronic leak detection systems as well. They're being used. What you need to do, though, is you need to go proactively and test these roofs. It's not continuous. So, but it's in fact a really good option to have a mesh laid in as part of your system. If it ever comes down to it that you have leaks, it'll be much easier to find the leaks and repair them. So quite a few options there, and I think they, really should be seriously considered when working warm roofs. So this is me, Babbage Consultants. If anyone has questions, even if you want to connect to have a coffee and talk about and get some ideas, I'm always keen to do that. So. Okay.
Stijn, thank you so much. Let's take into some questions. So what do you mean by damp closed in inverted commas? Please explain further.
Yeah, that's a little bit confusing. I agree. So damp and vapor is the same, right? So we use a little bit the same, but it's basically any moisture that is transported by air. That's what it means.
Okay, so a material that is closed to the passage of moisture or vapor.
Yeah, that's right.
Yep. Okay. So there's a couple of questions around that actually, because
Okay.
and not just because this is hosted by Proclimer, but the difference, and this has come up in several different ways of the questions being asked. But can you just explain the difference between a vapor barrier and a vapor control layer? And this
Yeah.
is not an advert for Intello, but it's about it's a little bit
Yeah.
about the definitions here. I think that's the best way.
No, I understand. I understand that. So vapor barrier is basically a barrier. Imagine like a plastic or something that stops the vapor traveling from one area into another one. I've always had this really nice example that was given to me by Kara from the Passive House, who basically was blowing on a piece of paper. And I invite people to do that. And if you blow on a piece of paper, you don't feel, of course, any wind, but you do feel with your hand the vapor coming through, right? And that's a really good example of how vapor, even if you're wind tight, airtight, you can still be vapor open, right? And this is so a vapor barrier is basically a resistance for vapor to travel from one side to the other. A controlled layer is slightly different, and that has to do with the technology that Proclima is offering, and very much with this slide. And I'm going to jump back a little bit, John. I spoke about the different types of condensation, and I mentioned inverted conversation. Now, that's, in my opinion, way more important for, let's say, walls than it is for warm roofs. But in the summertime, you can have the sun basically pushing moisture through your envelope to the inside, which is also something you don't want to happen at that time. And if you control that, you can make, or there are materials, and Proclima has one, where the temperature would be a factor of how much the vapor can travel through that layer. And it would be, for instance, quite open in the summertime, but quite closed in the wintertime, something like that.
All right, okay, let's move on. So what is the ballast material on the inverted roof detail? And maybe I can add something to that question. Why is there the risk of that being sucked off a roof? Like, where does that come from? Is that science, or is it just a scare tactic?
No, it's not a scare tactic. So I'll open it up. So literally, if you look at this insulation here, there is no fixing through that insulation. That literally is laying flat onto the membrane, right? It's not glued on, it's there. So you need something to keep it in place, some weight, because this is exactly what you imagine it is. It's a piece of insulation. It's very light. If there's a little bit of suction on the roof, it's going to go and fly, right? So that insulation is these little gravel stones, basically. That's what we use mostly. But it could be other products as well. But mostly it's gravel stones.
Cool. Okay. What about a cold, flat roof? Maybe you can pull up the slide, which is your cold, flat roof that with the skillion framed. Yep.
Yeah.
Well, it could be that one, but it could be the fully closed as well. I don't think that matters. How about a cold, flat roof with 100 millimeters of topsoil green roof? Is that a good idea?
So this one with soil on top. Is that the question, John?
I think so, or it could be the fully insulated skillion cold roof as well.
Yeah, so because you allow ventilation underneath, that topsoil is not doing much, right? Because you still have cold air basically at the same temperature as the outside air that's going to go underneath your green soil.
Right, so it's not doing damage, but it's not improving it either. Is that what you're saying?
No, it wouldn't be any different. No, it would be hardly different. Yeah.
Okay. And what about the closed?
It's the same as a cladding, and you have a cavity that's fully ventilated, but then you put a lot of insulation on the outside of the cavity in the cladding. It's not going to do much because the cold air is just going to short pass your insulation, right?
Okay, let's jump into something which is very similar to that, but it's about the Auckland climate. So this is relevant
Yep.
for everybody everywhere, but it's specific in that. So I'm interested in your thoughts around our humid Auckland climate and moisture control in roof cavities. Can there be too much passive ventilation of the roof space? So are we introducing air carrying moisture into a roof space, and is that a problem? And
Yeah.
then there's another portion of that: is any ventilation better than none?
Oh, yeah. So in cavities, ventilation in wall cavities is absolutely important, because we basically avoid any chance of interstitial condensation if you build that right. And that ventilation is really going to help you. And you could see in, let's say, the old glazer diagrams or the old visual tools that we used for predicting condensation, how that ventilation is really helping to take out any moisture that comes from the inside. The buildup of all these materials is obviously very important, but that ventilation, we know, is a massive factor in keeping your wall healthy. Now, if we go to the roofs, and there's still a little bit of confusion here. So in the old days, we had cavities here, but the building code basically did not want to open them on the top, and that was because they were scared that moisture would end up through the soffit into the roof space. And that is a fair point, but that tells, unfortunately, more about how weak our roofs are than how good our claddings are. These are different things. So what I believe the right solution is that you have a ventilated wall system with ins and outs on the top, right? So you have an inlet and an outlet. That outlet has to go to the outside, obviously, not into your roof space. And then in the roof space, well, we really need to talk about the current cold roofs that we've been using. And there's many things we can do to, let's say, aid any moisture that gets into that space. But I can tell you the shape of the roof is important, the way it's oriented, to which side, absolutely the ventilation. I'm very happy we see these suppliers coming with these little tools to give you minimum ventilation on the bottom and the top of your roof. At times, I think it may be in certain buildups, it may be necessary to have even a little bit of mechanical ventilation in that roof space just to keep it healthy and clean. And then it doesn't really matter, right? Then you basically create a healthy environment that's also going to be durable, right?
Stijn, we've got a load more questions in here, and we
Fantastic.
are out of time. Which so what we'll do is we'll
Yeah.
probably get those questions to you, and so that you can answer, and we can help if need be. But look, that is the end of our time today, and it also brings our Knowledge Zone webinars to a close. So thank you to everybody who has joined us. Look, we've had a combined total, including today, of 1,394 people join these webinars over the last 2 weeks. Now, look, that excites me, not for the numbers, but for the opportunity to broadcast a shared language and a better understanding of these topics across the industry. So a big thank you to our Proclimer team for working in the background. Thank you, Stijn, for walking us through the science of warm roofs, and maybe just a portion of all there is to know about warm roofs. So the definitions, the options, the benefits, the limitations. Brilliant. Thank you so much. So thank you, everybody, for joining us. This presentation will be online on Proclimer's YouTube channel within a day or two. And if you'd like to get hold of Stijn, as he said, feel free to contact him, or you can just get in contact with us and we can put you in touch if you can't spell his name, although it is on screen, so you should be able to. Thank you all. Thank you, Stijn. And that is the Knowledge Zone 2026 complete.
Well done.
Thank you and goodbye.
See you.